Thumbs up. All right. All right. Um, I will tell you, it is a skill that I am still struggling with to give these talks out into the ether like this. I have no idea what you're thinking or seeing, so I'm going to do my best. My goals here is to kind of talk about three things that I think are important topics. Kind of cover what's actually happening out there in the real world in ML today because there's so much hype, and I think that what's important to me is making ML actually work. Secondly, the difference between engineering and machine learning engineering, because I just think about that a lot. And then also wanted to talk about at suggestion of the organizers, talk about building products, for ML teams and how I think about that. So, I'll briefly kind of introduce myself and my career and my biases. I think these are relevant. I came from I started a company called Crowdflower Figure Eight back in 2008. And, back then, when you would try to raise investor money, you would hide the fact that what you were doing was related to machine learning. Machine learning sounded like a science project. And so I ran that company for about a decade. And then I started Weights and Biases, which is what I'm working on now, which we think of as a developer first ML ops platform. I hope some of our users are out there in the audience today. And I hope that if my talk is boring, you go to WNB.com, which is our website, and try our product, which would make me even happier than you listening to this talk. I'll say one more thing. Where a lot of this is coming from is, we've been recording this podcast with a lot of people working on real world machine learning projects for the last 3 or 4 years. And this has been a real lesson for me to get to see in lots of different verticals what's relevant to people in the machine learning space. So check out Gradient Descent if you have the time. I thought it might be fun to kind of talk about my very first machine learning stack that I built, because really my first job was essentially the ML engineer and the ML ops person and all that together, working for a company called Yahoo, which was super exciting back in 2004, 2005 when I was there. And the goal was to make the search engine results better. And at that moment, we were switching from a rule-based system to decide the search results to a machine learning system. And I was actually the person that deployed the code that ranked the search results for a lot of the Yahoo properties. And I was kind of reflecting back on what my stack looked like, which actually is not that different than what you'll see today. So I don't know if there's any R users in the audience, but back then, we would train our models in R typically, and we used the GBM library, which is actually still around. There's gradient boosted machines, but then there was no way to actually get that into production automatically. Now there's tons of companies that do this. Back then, what we would literally do is I wrote code that would take that R stuff and generate C code with like a whole bunch of go-tos, right? Because it was just automatically generated. And then we just check it into to production, which this was like before Git. And these files were enormous and they actually brought the version control code to its knees because it wasn't used to such gigantic files getting pushed in there. And then we actually had an evaluation set, which is something that people do now, did at the time, right? And we would run it on that. Then we'd do an A/B test and some of the traffic, and then finally we go into production. The whole process took months actually. So the development cycles here were months. But now we see in lots of companies they do on the order of days, but at the time it seemed fast. So it's amazing how much things have changed in 2005. There really were not a lot of applications when I was graduating and looking for an interesting job in machine learning. Now we see almost every company of a certain size is doing something in machine learning that really matters to them. I thought it might be fun to do a quick survey of some of the stuff that we see out there. First of all, I think everyone feels the impact of speech recognition, right? This is like the device that is like obvious to my mother, right? Like like now there's like Alexa and there's Siri, and we we actually interact them and kind of enjoy it. And there's this amazing graph that actually the Economist put together, which I really love because I think it sort of shows what's really happening in a lot of these machine learning applications. where you're moving from, you're just making sort of steady progress, right? So like here on this graph, lower is better, and it's showing kind of um, different benchmarks, and it is in log scale, right? But you see from like, 1993 to, 2016, just folks are making continuous improvement, right? But that's not the experience that we have as a consumer of ML products. I mean, sort of, you know, speech recognition goes from incredibly frustrating, like it was in the aughts, to how it is now, where it's incredibly impressive, right? And we're willing to sacrifice our privacy, many of us, to put it in our houses. Um, just some other examples that we see that we wouldn't have necessarily known would exist is this amazing example. This is one of my favorite examples from Blue River, which is a subsidiary of John Deere. And we we're actually just talking about them on the podcast in detail about how this works. But they are in fields in Texas with sprayers, and they identify weeds with cameras on these gigantic sprayers and hundreds of cameras. And when they identify a weed, they spray just the weed with herbicide. So it actually has like two huge benefits, right? I mean, one is that you can use a lot less herbicide, like a lot less, which is good for the environment and good for the farmers. It saves money, and it makes a cleaner world to live in, which is a huge deal. And it also makes the herbicide more effective because they can use different types of herbicide for the different types of weeds that there are. So it's not just like, is it a weed or is it a lettuce? It's like which exact type of weed is it? And there's an incredible amount of effort that goes into actually deploying this, right? So, I've been working with these folks since, maybe 2016, and it seems so simple, right? This seems like such an easy, maybe vision task. But you can imagine, like, you're taking this vision task and then you're deploying it into computers, putting them in the hot, Texas sun, right? And then like, putting a huge cloud of dust around the cameras and the technology. And so it actually is an incredible feat, not just the vision task, but the deployment. But the reward is a better world for all of us. And so I'm hoping that we see more and more stuff get deployed like this. I think another place where, this is just sort of reflecting on my career. When I was and I was working at Figure Eight, we had basically no healthcare customers, maybe a handful. And Weights and Biases is one of the biggest places that we sell into. And it's really exciting because, I mean, if any of you have family members that have had any kind of like serious illness, that like medicine is just like, it becomes like the most important thing that you care about. And so, I think drug discovery has gone from, basically a non-ML task to totally an ML task like everywhere. I mean, we haven't seen any drugs come through FDA trials yet, but there's a little bit of a lag here, I think, where the technology takes off. And then, you have to like make sure that, it's working and safe. But, I think we saw, some amazing stuff with Google's AlphaFold. And if I, could go back to grad school, I think this would be the thing that I would study, because this just seems like, kind of going from zero to a lot of impact in really short order. We see a lot of robotics and vision tasks, and the applications are kind of surprising, right? Like you wouldn't think that like you'd want to make an autonomous robot with good vision, and then the application would be, kind of looking at where stuff is in the supermarket. But commercial applications are funny, and now you can actually go to a supermarket and see a robot, really doing something, really using ML to navigate and to check what's in its world. We see, medical imaging tasks of all types, but I mean, this is one where it's looking at cancer cells and trying to make prognoses. And eventually maybe this will turn into to diagnoses, right? To sort of see what type of cancer you have, how bad is it, and all that. I kind of love these medical imaging tasks, especially because it's something that the human bar is lower, right? Like we're designed to navigate through the world. We're probably not designed to look at gigantic images from microscopes and figure out exactly what type of cancer we're dealing with. So it seems like there's a real opportunity for computer vision to make a real difference in people's lives. And then of course autonomous vehicles is world changing, and even things like we see credit scoring. So we just see such a breadth of applications. It's totally different from when I was graduating, and the main applications were essentially go work for a hedge fund and try to make a little bit more money, or go basically work for Google or Yahoo, and rank search or rank advertisements. So anyway, I think it's a really, really exciting time to be in the ML space. And it's an important time to kind of ask ourselves this question, like, how is ML different than engineering, right? Is it just sort of a subfield of engineering? And I'll say some people do think that ML is just sort of like a subfield of engineering, and it's not that different, including one of my podcast guests. If you want to get the counterpoint, to me, you can look at this interview I did with Anantha Kancherla, who actually made some really smart kind of points on the other side. But I really believe that ML actually requires kind of fundamentally different processes and techniques. And so I'll sort of make that case. I think, the first thing is that, it sort of like rips up the whole stack. Like, back when I was in college, we barely studied, compilers. I remember I would run into like linker errors and I'd kind of just give up. And I didn't see linker errors, from like, I'd say, 2005, my first job, until maybe 2015, when I started to kind of come back to deep learning. It's like, okay, they've swapped out that CPU with a GPU. And so it's kind of, they've gone like deep into the stack and made some changes. I mean, I don't know how many of you struggle with just installing CUDA. Like when we put out articles at Weights and Biases on these kind of simple, practical topics of sort of like low-level setup, they end up always being our kind of most popular content, because I think it's actually just so hard to get stuff up and running in a way that it kind of got easier for a few years, and now it's kind of harder again. And we need to kind of really fix the sort of like low-level setup of machine learning. But maybe more importantly, I think the code that you generate for ML is actually really different than the code that you generate in standard engineering. And I guess like you can sort of see it here on the left and the right, of like, on the left you have like, code that I wrote, right? It's like it's Keras, to generate an ML model. And then on the right, you see the ML model that I create, right? So like, people often ask like, why don't folks use Git for version control for their ML models? And, there's a couple of reasons, right? They're just practical reasons. It's different, right? So the ML models, they're like giant files, right? So like, the version control breaks. These files don't diff, right? So like, code, like you could change, one line, and the code might, function in a new way. With an ML model, I mean, you could train the same model and the same data, the same time, functionally identical models. Like you couldn't find any difference, but like literally every character in that file is going to be different, right? So you don't get that same diffing. And obviously, like, we write code sort of for computers, but really we write it for each other, right? To kind of understand what we're trying to do. And so there's just no inspectability, explainability is such a problem in machine learning. And so I think what this creates is kind of fundamental difference between like writing code that runs like a recipe versus writing essentially code that creates a world for a model to learn in. Kind of means that debugging is a lot more science than engineering. And I like love this this slide from Andrej Karpathy. He actually presented it at a Figure 8 conference many years ago for the first time. And it talks about how the training didn't really set him up well for the work that he does, right? Like in his PhD, spending all of his time looking at models and algorithms, very little time looking at data sets, right? But then when you're doing actual ML in the real world, you spend most of your time kind of tweaking data sets, to make the model work and trying to see what it's doing. And I think it's kind of telling, some of the explainability stuff, right? Like, to try to figure out what a model's doing, you often act more like a scientist, right? So you'll end up, this is like a really interesting thing from a paper that I see a lot of people doing intuitively, right? Where you have a network trained on ImageNet, and then it's looking at, this picture on the left of a person, I guess, with a dog mask, playing guitar. And so, it says electric guitar, acoustic guitar, and Labrador. And so, acoustic guitar and Labrador is accurate in some sense, and then electric guitar is not. And you look at which pixels, if you removed them, would change the model's confidence the most, right? So you can actually see which pixels the model is then using to make the decision of electric guitar or acoustic guitar or Labrador. And so you can see the fretboard is actually the thing that makes the model think that it's electric guitar inaccurately, right? So it kind of makes sense. A fretboard and electric guitar looks a lot like an acoustic guitar. But in this sense, we have some sense of explainability, but the explainability is really coming from, not like inspecting the network like we might used to do with like a decision tree or even sort of with a random forest. They're really just coming from like observing what the model is doing in practice and trying different mutations of the data that the model is looking at to get at explainability. It feels again a lot more like kind of science than engineering. I should say, I want to put a bunch of like links here to stuff that I think is really good content if you want to learn more, since this is a little more of a survey talk. But when you think about debugging models, there's like so many different things that could go into it, right? But the output is always basically that you get a worse model, right? And so this website fullstackdeeplearning.com has a ton of free content on this topic that I would like really encourage you to kind of check out. And they have like actually really prescriptive ideas and best practices for looking at how to figure out what's going wrong with a particular model. And the challenge is that, right, it can be over derived, right? So like, you can have bad hyperparameter choices and bad data set construction and bad data model fits. And if you fix any one of them, it's not going to make your model performance increase. And you get these like absolutely maddening bugs. I thought it was funny actually in these lecture notes, they talk about this bug that I've actually personally encountered. So here's a little aside. If you run into this one, I could save you weeks of time because this actually cost me over a week to get to. So the glob, the Python glob function is actually not deterministic in its order, right? So if your features and your labels you're both getting from running this glob command, they're going to be out of order, right? And so when you train, you're actually training on noise, right? Because your features and your labels here are not matching. And it's just funny. I mean, I literally spent like a week just like banging my head, like trying like every possible, tweak to figure out what was going on. It turns out actually the guy, Josh, who runs Full Stack Deep Learning, encountered the exact same error and got stuck in the exact same way. I think there's another kind of practical issue. I mean, these days I spend a lot of time with like executives that are trying to get ML to work. And I think like the root of a lot of the problems here is that we actually have terrible intuitions about what's hard and easy for ML. And so like I love this example from the movie 2001, which came out in the late 70s, right, where a computer plays the astronaut in chess and beats him in chess and also kind of makes fun of him, right? And it's fun to watch this clip of this movie. It's funny what people thought were hard and easy back in that day. And it turns out actually that they almost removed the part where the computer beats the astronaut in chess because it seems so unrealistic. But no one thought it was unrealistic that the computer kind of banters casually with the astronaut. And I think it's like really telling, right? Because actually it was not that long after this the computers got better than humans at chess, right? That happened in the 90s. But I mean, I think the casual banter is almost an AI complete task. Like I've not had a computer make fun of me in a convincing way still, and it's over 20 years after that. So I think we should just always acknowledge that, look, like, the best scientists, the smartest people, we don't know what's hard and what's easy. And inside of teams trying to accomplish some specific business objective, we also don't know what's hard and what's easy. I'll give you another example. This goes back to my figure eight days, but I did a Kaggle competition. If you guys don't know what Kaggle is, you should go check out Kaggle. It's an amazing site where you can kind of crowdsource models, and so you can have lots of people kind of try your task and see what the best performance is. So I had a task. The task was actually a search relevance task, and the accuracy went from 35% to about 60% in just an amazing, such a feat, right? Like I was so excited to see that, and I kind of wondered how good the accuracy would get, and actually expand this out, for another, month or two, and it completely flatlined, right? And so I think that there's a real lesson here, because actually you might think, well, maybe people got bored, they weren't like trying this task. It turns out more and more teams were trying to win at my task, and this is a typical curve that you see in Kaggle competitions where you get, diminishing returns. But if you imagine you're kind of the manager and you're seeing this graph, you're getting really optimistic, and then you're seeing this graph and you're getting really frustrated, right? And this is like the best you could possibly do because there's like thousands of people around the world all competing to do this task as well as possible. And so, this is not just like in your stand-up that you get these projects that run long, right? I mean, you see like, in self-driving cars, even going back to 2015, you get these exponential looking curves. And then I've been presenting this slide for years, right? But you look at this is also in 2015. Elon Musk drops his prediction of autonomous driving from 3 years to just 2. I remember thinking at the time, that seems a little crazy. Like I wonder if we'll really see that, right? But I don't think that we have autonomous driving, still today, right? But you can imagine kind of looking at this exponential looking curve on the quality of the self-driving. You're thinking, wow, like this is about to get solved. And we look at, other exponential curves as startup CEOs, like, like user growth or things like that. You can kind of extrapolate them out, right? So I think, ML is particularly hard for executives in startups to reason about. I say that as one. There's also this reproducibility crisis, which I think everyone kind of understands now, right? But there's this real challenge, to even reproduce any of the academic results. And I know this because I've tried to reproduce, many of them. And Pete Warren, I think, did a great job of naming this machine learning's reproducibility crisis. And we actually just had a conversation on gradient descent about this, right? But you see like all these different places that come from. Whereas stochasticity can break in, right? Like, I mean, I'm used to like, you set your random number seed and you're done. I actually think like true reproducibility at this point is almost impossible, right? Like the GPUs just existing and just kind of sending data in different orders. If you're working even with one GPU, it can be very hard to make your model completely reproducible. That said, I think like everything that you do to add a little bit of reproducibility to your model, it helps you in many different ways. You really can't have explainability without reproducibility. You can't have auditability without reproducibility. I don't think you can really say that you're doing real high quality engineering without some sense of reproducibility. And so there's actually a really great checklist put out by McGill that I think as many of these things as you can check, you'll be able to reproduce it better. But I think like the problem is getting harder, not worse. And I mean, I think Andrew Ng, kind of early said this, in a very clear way that basically, as we get like more and more data and more computation available, the scale just increases, right? So the reproducibility problem and the explainability problem just gets harder and harder over time. And you see this in the, exponentially increasing resource consumption. And, I've been talking with like a lot of journalists and others now about like, hey, what do we do about this, right? Like, we keep seeing kind of more and more, resources getting used for these models. Like, what if we made these models kind of, simpler, like easier to train? Will that lower the resource consumption? And actually, I don't think it will. I think this is the underrated graph from the same blog post that OpenAI, put out a while back, which shows that, basically, just to get AlexNet level performance, you need less and less compute resources. So actually, our algorithms are getting a lot better. Right, where every year we need less resources to get to a certain quality of performance from an algorithm. But that I think actually just inspires companies to use even higher levels of compute because the benefit then is even higher and there's more compute available. So this I think is an increasing problem for environmental concerns, but also maybe more importantly, just being able to reproduce any of the academic work that's out there. And you see like an increasingly complicated dependency graph, right? Like, I mean, back in the day, you would kind of train in one set of data and just deploy it. But now we see that like most things, like a self-driving car, for example, tries to break all the different things that it's doing into different subcomponents, right? And so, what happens is, over time you have different subcomponents with different release cycles, and they can accidentally mess each other up. And another thing which we used to talk about is like something people should really do, transfer learning. It's kind of gone from a research topic to just table stakes that I think everyone does today because the performance is really incredible. And there's nowhere that it's more impressive than with essentially word embeddings and things that you see like, originally BERT, now GPT-3 and some of the models in Hugging Face. To the point where, you'll see people that are essentially, calling themselves prompt engineers, right? So they're saying, look, like my goal is not to like train the model, it's to put the right prompts into a model to make the model perform the specific task that I want, which seems to work particularly well in the NLP domain. And then kind of before moving on to briefly kind of the stuff that I'm working on, I should mention that, I think responsible AI is becoming more and more critical to anyone that's actually deploying stuff into the real world. We see, daily issues of like bias creeping into models. And I just wanted to point you to, I think Alyssa Simpson put out a really excellent book on, kind of a breadth analysis of all the things that you'd want to do to deploy AI responsibly. So I think in the last, 3 minutes here, I want to kind of talk briefly about, what I'm working on at Weights and Biases. The thing I was seeing, I started the company is like, man, there's all these like great tools for the developer workflow where, we kind of know what the workflow is. And I think we kind of know what the workflow is now for, ML developers. But, what I see ML developers doing is basically custom things, text files, shell scripts. Even though there's starting to be stuff available, it just doesn't seem to like pass that bar where developers really want to use it. And so, the goal with Weights and Biases was to make essentially developer tools that people could pick and choose from, use the best of breed thing, and kind of just solve the specific issues that they're running into in the production, the real world workflows. I should say there's a lot of other approaches to ML ops. There's, kind of like auto ML where it's like, look, we're just going to like automate the whole thing and you're not going to need to worry about it. Like maybe we don't even need the ML engineer. Kind of interesting, but I don't think that's like where most companies are headed right now. There's also like a lot of pre-built models, also really exciting. That's definitely not what we do. I think the pre-built models often, really impressive, but hard to get to use for like an individual specific use case. And so, we haven't been around that long, but I will say we work with thousands of customers that I feel really proud of. I mean, I think like, it's amazing to see how many different industries are doing real world ML applications where they're using Weights and Biases. And I think they pick us because of like really, really good focus on interoperability. We work with we work with more open source repos, I think, than any other MLOps product on the planet. And I think we've done a really nice job of making strong principles that we stand by, right? So, the key here is we want the integration to be super simple because we know people are busy. There's a ton of different things they can try. And we've really worked to get that integration down to a tweet length. We really want to make the ML developer, ML practitioner, ML engineer successful. And we want to be something that they really want to use and makes their life better in all the stuff they do. And then I think one thing that I think other ML ops platforms miss is like collaboration and reproducibility is really critical, right? As teams grow, they need a way to kind of share the results of what they're doing, and it feels really good to help them with that. So a lot of reproducibility is not like a computer science problem. It's like a human problem, right? Of making it really easy. Like, everyone kind of knows all the steps that they should take to make models reproducible, but it's a pain in the butt, so you don't do it, you forget about it. And if you kind of miss even one of these things on the checkbox, then it's not really reproducible machine learning. So I'm running a little bit, I know I'm running a little bit over time here, but I wanted to say, for folks that want to learn more about, ML engineering, there's 3 things I'd recommend you check out. I think FastAI has incredible courses, and we love them. Kaggle also, now actually has courses too, but like I think gives you like real applications to get your hands on doing ML stuff. And then, the Weights and Biases community, we're hoping to build a community that's really welcoming people of all skill levels, and we'd love to see you there at community.wb.ai. So yeah, I think I'm right at the 30 minutes to maybe open it up to questions from there.